The purpose of any electrical circuit is to provide power to perform some useful task. Electrical power consists of a combination of voltage and current. So an engineer's job ultimately is to interconnect electrical components in order to get the voltages and currents where they need to be in order to provide the power necessary to do the task at hand. This video introduces basic concepts relative to all of the circuit components we'll be using in this class. All electrical circuits, no matter what their purpose is, consist of interconnected circuit elements. These elements are interconnected at their terminals. For now, I'll only talk about circuit elements that have two terminals. This is a picture of a generic two-terminal circuit element. The current I flows into or out of the circuit element, and there is some voltage difference V between the terminals. Every circuit element is mathematically described by a relationship between the voltage and the current at its terminals. Voltage is an energy level difference between the terminals. This gives an electromagnetic force which can be used to move charges from one terminal to the other. It can be useful to think of the voltage difference V as causing the current I. So if V changes, so will I, and the circuit element's properties relate these two parameters. There are a few basic properties that all of our circuit elements will have. One of these is that none of them can store or accumulate charge. So any current entering one of the element's terminals must be balanced by an equal current leaving the other terminal. Circuit elements can be divided into two basic types: active elements and passive elements. Active elements provide energy to a circuit from a source that's external to the circuit. For example, a battery performs a chemical reaction to create electrical energy. From the standpoint of the electrical circuit, the energy appears out of nowhere. Energy from passive elements can't come from outside the circuit. They use energy that already exists within the circuit. For example, capacitors can store energy provided to them from a circuit and return that energy to the circuit, but the energy doesn't just appear from nowhere. Circuit elements are modeled mathematically by relationships between the voltage and the current at their terminals. These relationships are called the element's voltage-current characteristics. If the relationship is presented graphically, the plot of current versus voltage is called the voltage-current curve, or the IV curve. Since the voltage-current characteristic governs the relationship between voltage and current at the terminals of the element, it tells us what current will correspond to a given voltage difference at the terminals. We use the mathematical function relating voltage and current when we model the behavior of the circuit element. This course focuses primarily on the analysis of electrical circuits. The goal is to predict the voltages and currents in the circuit based on mathematical models that predict how the circuit should behave. So now I want to give you a brief overview of how we go about analyzing circuits. We need to be given the circuit elements and how they're connected to form the overall circuit. Mathematically, we represent the circuit elements themselves by the voltage-current characteristics at their terminals. The way the elements are connected governs the interaction of the elements with one another. These interactions at the element's terminals are described by the basic laws governing energy transfer in electric circuits: Kirchhoff's current law and Kirchhoff's voltage law. Combining the equations governing the components with the equations governing their interactions allows us to predict the behavior of the circuit. Designing an electrical circuit uses many of the same tools as circuit analysis, but the approach is reversed. In circuit design, we know what behavior we want from the circuit and the fundamental equations governing circuit interactions. Therefore, we have to choose circuit elements that have the appropriate voltage-current characteristics and interconnect them in a way that will create a circuit that performs the desired task. Unsurprisingly, any circuit design is followed by an analysis of the design to verify that the circuit behaves the way it was supposed to. The final step will be to build and test the circuit to make sure our math was actually correct. The next video presents the sign convention that we have to follow when defining voltages and currents for passive circuit elements. After that, I'll define some voltage-current relationships for a few common circuit elements.